Are you ready for this one? 111 Desmos lab. I don't think you're ready. This is too tough. I don't know. There's a lot going on in this section. Let's see what we can do. I hope you're having a great day. I hope that this music got you psyched the way it did for me. Let's chat about 111. What do you know? Recall that we've worked and seen a bunch of sequences. Our job now is to add all the things we've seen about sequences and patterns and tie them together, being able to now figure out what the table looks like, an explicit equation. Don't forget the graph. You can do that too when we're on the right page. Don't forget the graph. Don't forget the explicit equation. Recall that we can knock those out if we know our previous term, and we can take it further from there. We can also talk about constant ratios, or constant difference, or common difference. I don't know why they call it constant, but that's one way to think about it. Any missing terms, the types of sequence, story context, that's going to be us this whole time. It's just talking about these sequences and seeing everything that we can say about them, at least a minimum of 4, but I'll leave it up to you to kind of get the rest. So let's dive right in. Are you ready for this? I know that the recursive formula for the sequence is f of 1 equals negative 12. Ooh, I could show that in a table. You might say, what? You can? Yeah, you can. F of 1 is negative 12. Boom, just like that. That's one thing. And this is what kind of equation or formula? Hopefully you're saying recursive because we have this f of n minus 1 in here. So this is saying that our current term equals our previous plus quattro. So if our previous term was negative 12, we can add 4 to get our next term, so negative 8. Keep that going to get negative 4, then to 0. These would be the third and the fourth term. All right, that's a table. Our common difference, which I'm going to abbreviate as CD, is going to be positive 4. Missing terms, we found some of those here with 2, 3, and 4. Those outcomes there. What else can we get? We can't get a common difference. We could get a quick graph. We would need to find our 0 term, though. Can we get a hold of that? Sure can. Hopefully you're saying that we would start down at negative 16, and then it would just keep going from there. Not the best graph in the world, but it's all right. And we see that when x is, or n is 4, it intersects on the x-axis. So this is n, f of n, or if you want to use x and y, that's cool too. So we got a graph and we got some of those points, and all right, cool. I'm sure you could say some more things about that. 2, we got 5 terms in the sequence. This is subtracting 6, subtracting 6. So right off the bat, I can say my common difference is going to be negative 6. What else? I know that I could go and talk about this in words, saying that it's going to be the current is the previous minus 6. So that's in words. I could then take it further and say that f of n equals f of n minus 1 minus 6. I know that f of 1 is going to be 0. So that's our recursive. 2 interpretations of our recursive in words and also in function notation. What else can we do? We can get the next few terms. That's cool. So we could keep this going, keep subtracting 6, get negative 30. Keep it going, subtract 6, get negative 36. So those are some other terms we could have thrown in. We have this explicit formula for the sequence, -10, 3 to the n. What do you know? What you know about that? Well, I know that this is using n f of n. I'm going for the table because I think it's easy to just plug in numbers for that. So I know that if n is 0, we would have -10 times 3 to the 0 power, which is -10 times 1, which is really just -10. So that's one point we found. We see that if it's 1, this is going to be -10 times 3 to the first power, so -30. Oh, I think I see a pattern coming up. Let's keep it going, though. If this was 2, I would have -10 times 9, which is -90. Oh, I think we have enough here for a pattern. So hopefully you're seeing that we're taking the previous term, multiplying it by 3. So notice the jump from -10 to -30, you have to multiply by 3, or also -30 to -90, multiply by 3. And that gets us our current. So that's in words. We could say an explicit equation where f of 0 equals -10. And so in function notation, f of n, what do you think? What can we put in here? Well, we're talking about our previous term, so let's use f of n minus 1. Multiply that with 3. Got a nice little explicit equation there. This is actually given as the recursive, which is fine. Just noting that it's recursive, we can plug in any number for n. We can get a common ratio of -30 over -10, which is +3. So that's our common ratio, or in this case, they call it the consistent ratio. I'm open to both, though. So we got the table, we got in words, we got explicit, we got our common ratio. Cool, I'm with it. Next, 234.5, 6.75. Interesting, okay. Well, this is just adding 1. And then this is adding 1.5. This is adding 2.25. All right, so it's definitely not an arithmetic sequence. So it must be geometric, or maybe there's none. So this is geometric. First thing I'm going to do is find my common ratio because I don't know consistently what's I don't know what's happening with it. So I'm going to say maybe geometric, but it might, you know what, actually, I don't know. Let's try it. Yeah, it's got to be geometric, actually, because they're not adding the same thing. So let's backtrack that. Yep. All right, common ratio, 3/2. So this is taking the common ratio of 3/2. And so maybe that's what's happening here, is that every time we're taking the previous term and we're multiplying it by 3/2, or 1.5 if you're a fan of decimals. And that gets us our current. So that's in words. That's the second thing I'll use. Next thing, f of 1 is equal to 2. So f of n equals f of n minus 1 times 3/2. Pretty cool. What else do we want to get? We can get more terms in the sequence. We could also sketch out that table. For this table, I'm going to get a hold of the 0 term after I plug in the rest. So this would be 2, 3, 4.5, All right, so I know that this was 2 times 3 halves. So that means that this was some number times 3 halves. How can we get a hold of what the previous term was? Well, if this is multiplying, the previous term's multiplying by 3 halves to get 2, we could use division. So we could do 2 divided by 3 halves, which we can rewrite with fractions using the reciprocal there. Flipping the fraction, getting us 4/3. Pretty extra to do that. But that's the fourth thing that we could look at. Fractions, woof. Could have also written it as 1.3, but it's all good. Arithmetic sequence, and we have f of 3 equal to 10, f of 7 equal to 26. I think a table is going to work the best here, even just to showcase and show off the points that we have. Trying to flex on all those math people out there. Okay. So this is going to dodge a few terms. So I'm just going to keep writing in what should fill in between 3 and 7. But I know that here it's jumping to 26. Interesting. All right. So I know it's arithmetic, which means that from 10 to the next bit, it's going to be probably adding some term because we're going up to 26. Same here, also adding. And then finally adding there. Well, let's see. I'm jumping from 10 to 26, and I have 3 numbers to hop between. I know that the difference between 26 and 10 is going to be 16. And I'm jumping from 3 to 7, so that's 4 numbers. So hopefully it's going to be adding 4 every time. Let's just double check to make sure that's the case. 10 plus 4 gets you 14. 14 plus 4 gets you 18. 18 plus 4 gets you 22, feeling blue. Finally ending at 26, getting our kicks. All right, so what did I do? I made a table. I actually got my common difference. So that's one thing. I made the table. I got a hold of these terms that I didn't have before. So that's a third thing. Can we get a fourth thing? Sure, we could. You could say something, well, I mean, f of 3, I don't want to say f of 3 is the starting point. We could go back to f of 1. Because in this case, if n was 2, our outcome here would be 6. And then if it was 1, just deducting 4 more, that'd be 2. So then we would say f of n equals f of n minus 1, just plus 4. So that's our explicit. So psych, recursive. So that's the fourth thing that we got. And again, this is optional what you go with, but you could graph these. I think that's another great option to follow with. 6 I'm going to skip so that I get you out of here quicker. I have a sequence where f of 1 equals 5. Nice table here may help. So f of 1 is 5. Constant ratio between terms is -2. Interesting. So I know that as I move from here to here, I'm going to be multiplying this by -2. So jumping from 5 to the next term, 5 times -2 gets you -10. Keep jumping ahead, times -2, getting you 20. Keep jumping, -40. So we see that this is jumping back and forth between negative, positive, negative, positive. It's cool. What else? This is definitely a geometric sequence because we have a common ratio. Table was cool. Common ratio was given to us. What else? It's definitely not arithmetic, and there's no common difference. Let's backtrack to recursive. I like recursive. Okay. So our starting point here is f of 1 being 5, and then f of n, again, is the previous term times -2. If I wanted to get the 0 term, what times that? What times negative? Pretty much I'm asking what times -2 will get you 5? What do you think for the 0 term? Hopefully you're dividing both sides by -2. That cancels. So the 0 term in this case is -5/2. It's cool. What else can you get? I mean, I kind of got a lot. I got all these terms in between. You know what? That's actually a good amount. Sequence models the value of a card that originally cost $26,500 but loses 10% of its value after every year. This sounds reminiscent of Augustus and his candy from 1.7. So I'll have this table denote the year of the car and then the value. So originally, year 1, 26,500. So we could also call that f of 0. Start to build our recursive equation there. And what else? This is 10% as this keeps going. So in year 1, we're taking 10%, or we can call this 0.1. So we're taking 26,500, multiplying this by 0.1. Next year, we're doing the same thing, 26,500, but now multiplied again by that 0.1. Same thing here. How many 0.1s do you think we're going to have? Hopefully you're saying 3. Are you starting to see a pattern here? Where we have 26,500 and that 0.1 keeps changing depending on the year. Here it's being squared. Here it's being cubed. Okay, makes sense. All right. So we could probably assume that for our explicit for year n, we'll still have 26,500, but depending on the year, it's going to be lots of 0.1s. So we'll call that to the n power, because that's the thing that keeps changing. For our explicit, we can say that this is f of n equals the previous term, but times 0.1. Again, 0.1. Oh, yikes. Remember that we're subtracting the 10%. So make this actually 0.9. Forgot we're losing 10%. So this should be holding on to the 90% of the value. So remember, 1 minus that 0.1 gets you 0.9. So we're retaining 90% every year. Of course, it's going to keep going down, but it's helpful. This is definitely a geometric sequence. We've got the table, we've got the recursive, we've got the equation, and common ratio is going to be 0.9. That's nice to know. So we got a few different things. 2 more problems. Can you dig it? I know the first term of the sequence is -2, fifth term is -1/8. Oh, it's jumping all the way down to -1/8. Woof. All right, that's fine. Can't stop me. I still have the second term, third term, and fourth term in between. Wow, this one's challenging. Well, I know that we're just adding 1 for n, so this should hopefully be consistent change. Interesting. That's kind of tough because we only have those terms. Well, maybe if I rearrange this, I know that this is -1 over 2 to the third power. And I know it's retaining the fact that it's negative. And I know that if this was graphed out, this would be going closer and closer to 0. It's probably gonna be like that. Potentially. Well, I have a quick graph. That's one thing. I have rewritten this. Well, let's see. Maybe this exponent here is 2 less than n. So maybe this is -1 over 2 to n minus 2. Is that possible? Is that legal? Can I try that? Well, let's try if n was 1. If n was 1, you would have -1 over 2, 1 minus 2, which is still -1 over 2 to the -1 power. 2 to the -1 power can be rewritten as 1/2. This can be rewritten as -1 over 1 multiplying with 2 over 1. So that gets us -2. Lo and behold, this is our explicit equation. There you go. Got that quick graph. I got that table. Got the explicit. Yeah, that's enough for that one. You've seen a lot of this. There's so much here. What do I know? I know that this is linear. It's a straight line when graphed. I know that this is arithmetic. I can get a hold of the slope. I sure can, trust me. I know that this is going to be 0.11. And I know that this point here is 3.9. I know that I could get to that point by running 3 going down 2. Yeah, that's right, going down 2. So in this case, I could say that my common ratio is going to be this -2 over 3. Oh, sorry, common difference. Because we took our rise over our run, -2/3. So common difference. I know that I could keep this going and going. In words, I could say that the current is the previous, and then subtracting 2/3. Oh God, more. There's a lot. Explicit, I know that f of 0 is 11. So f of n would have to be equal to f of n minus 1 minus 2/3. I could also use the explicit and say that I'll use f of n and n. I hope you don't mind. We're starting at 11, but then we deduct 2/3 depending on the n input. So we could also call this negative 2/3 n plus 11. We'll see more graphing in the next section. But I think that this is a lot. We got the recursive. We got our common difference. We got the type of sequence. And we got our explicit. Wow, that's a lot. All right, well, I'm going to retire for the day. There was a lot here. Thank you for keeping with me. If you kept with me, reach out if I can help with anything. Thanks for watching.